Hello everyone. So today we are diving into a super interesting topic, the Java memory model and how it affects multithreading. Okay, so here's what we'll cover in this video. We'll cover what are registers L1, L2 and L3 caches. We'll also see how these caches can actually cause problems in a multi-threaded environment, which leads to race condition. Post that, we'll also look into a simple code example that shows the race condition issue in action. Okay, and finally, how to fix that particular problem with Java tools like Volatile and Synchronized. Okay, so let's get started with understanding what registers L1, L2 and L3 caches really are and why they exist in the first place. So let's look into registers. So registers are the fastest and smallest memory units inside the CPU. Okay, so they are very tiny in size, they just have few bytes, and they are the fastest when compared to L1, L2, L3 cache and as well as main memory. Okay, so memory access for registers are the fastest. Okay, and they are used to hold the data that CPU is actively working upon. Okay, so used during instruction execution. For example, consider CPU has to execute an instruction int c is equal to a plus b. Okay, so what happens is value of A and B are loaded from the memory into the registers. Okay, and post that the plus operation happens on the registers itself, right? After that operation, result C is calculated, and then this C will remain in registers until it is flushed inside the main memory. Okay, so registers are used because CPU can't compute on anything else. Okay, so whenever instruction execution happens, all the variables which are associated with that particular instructions are brought into registers first and then the operation happens. Now let's look into the L1 cache. Okay, so L1 is the first layer of CPU cache which is closest to the CPU core. Okay, and it is used to store recently accessed instructions and data. So it is very small in size and it is also very fast. So it is faster than L2, L3 cache and main memory but slower than the registers. Okay, and it is used for frequently used variables. For example, loop variables. Okay, so for int I equals to 1, I less than 100, I plus plus. So this I is accessed very frequently, right? So that is where L1 cache is used. So value of I is stored in L1 cache itself. Okay, so it totally depends on discretion of CPU, but mostly this is what that happens. Okay, so L1 is the first layer of data access, right? So whenever, for example, in this particular example, for fetching the value of A and B, first what CPU will do? CPU will check in L1 cache. If it is present, then it will fetch from there itself. If it is not present in L1 cache, it will go into L2 cache, then L3 cache, then main memory. Okay, so this is what the hierarchy order is. We'll see later, but this is how overall it works. Okay, now let's go and look into the L2 cache. So L2 cache is larger than L1 and holds the data that didn't fit in L1 cache. Okay, so it's like a second chance for data, right? If data is not present in L1, then the CPU will go ahead and check in L2. Okay, and the size of this cache is medium. It is around 256 KB to 1 MB per core. Okay, so every core has its separate L2 cache. It is slower than registers and L1 cache, but it is faster than L3 cache and main memory. Okay, its purpose is to store slightly older data, or we can say less frequently used data. Now let's see L3 cache. Okay, so L3 cache is used as the last resort to check for data before going into the main memory. So if L1 and L2 both miss, then we check in the L3 cache for the data. Okay, and one very important thing is L3 is shared across all the cores. Okay, so all the cores of the CPU have same L3 cache. So registers and L1 and L2 cache were separate for different cores, but L3 is shared across all the cores. Okay, so since it is shared, we use L3 cache for inter-thread communication or shared memory access. Okay, so when I say we use, I mean to say CPU use it for inter-thread communication or shared memory access. The size of L3 cache is larger than both L1 and L2. It's around 2 MB to 50 MB in total. And speed is slower than all the three registers L1 and L2, but it is faster than the main memory. Okay, now let's move forward and see main memory. Okay, so RAM, or you can say main memory or memory. Okay, so in further videos, whenever I say RAM or main memory or just memory, it means the same thing. Okay, the main memory. Okay, so when the data is not present in L1, L2 and L3 cache, then finally the data is accessed from the main memory, and it is the slowest of all the caches. When compared to L1 cache, L2 cache, L3 cache, main memory access is the slowest. Size of RAM can span up to various GBs, 4 GB, 8 GB, 16 GB, 32 GB, okay? And one more important thing is it is shared across all the CPU cores, okay? So we saw what? We saw registers L1, L2, L3 cache and main memory. Okay, so what is the most important thing? Most important thing is, okay, so if there are two cores C1 and C2, so registers for C1 will be specific to C1 and for C2 it will be specific to C2. So registers are specific to cores. Also L1 cache is also specific to cores. L2 cache is also specific to cores, but L3 and main memory, these are shared across all the cores. Okay, so these two are common and these three are separate for each and every core. So this is also very important. So the CPU always looks for data in this particular order. It first checks in registers, then L1 cache, then L2 cache, then L3 cache, and then the RAM or the main memory. Okay, now let's see this. We have a very nice comparison table here with analogy. So this is to summarize what we have discussed till now. This will be available in the notes which I will share. Okay, so one thing I want to highlight, if you see here carefully, we can see inside the CPU core and on the CPU core. Okay, so registers are present inside the CPU core and L1 cache is present on the CPU core. But what is the difference between these, inside and on the CPU core? Okay, so inside means these are the components that are part of the core's execution pipeline itself. Okay, and on the CPU core refers to the components that are physically located on the same chip area as the core but not part of the instruction execution unit. Okay, so if we take an analogy, so the chef has knife in hand, right? So those knives can be considered as registers, but the ingredients which are kept on the counter, those can be considered as L1 cache. Okay, so it is basically on the same chip, right, on the at the same place, but not the part of core execution unit. Correct. So execution unit is what? Whatever chefs have it in knife and whatever he is cutting. But the ingredients which are kept on counter, those are not actually executing it but present at the same place where the chef's knives is present. Okay. Okay, now let's look at this diagram. So we have two cores, core 1 and core 2 here. Both of these cores have separate CPU registers. Okay. Apart from this, they also have separate L1 cache and L2 cache of their own. They have a shared L3 cache, and apart from this, a shared memory in which there is stack as well as heap. Okay, now assume we have two threads running on separate cores. So thread 1 is running on core 1 and thread 2 is running on core 2. Okay, and suppose we have a shared object in heap having a variable count equals to 1. Okay, so obj.count equals to 1. Now suppose thread 1 reads the value of count, okay, reads the value of count, stores it in its register here, count equals to 1, and then tries to perform an increment operation on it. Okay, after storing in register, it tries to perform count plus plus, right? At the same time, at the time when this is performing this operation, thread 2 reads the value of count from the heap. It also stores it in its own register, count equals to 1, and performs the operation count plus plus. So at this particular point of time, for thread 1, the value of count will be 2 and the value of count for thread 2 will also be 2. But the actual value should be 3, right? 1 incremented by thread 1 and post that it should be incremented by thread 2, right? So final value should be 3, but the actual value is 2 both with thread 1 and thread 2. Okay, so after incrementing, whichever thread writes the value of count at last in the heap, that particular value of count will be updated, right? So irrespective of whether thread 1 writes or thread 2 writes, the value of count after increment will be count equals to 2. But this is incorrect. So this is one of the way in which race condition happens. Race condition first cause is simultaneous access. Okay, now let's look at second condition. Now suppose first let's erase this. Okay, now suppose thread 1 is reading the value of count from the heap. Okay, it has read the value count equals to 1. It has incremented also count plus plus to count equals to 2. But this count 2, we cannot guarantee when this particular count 2 will be written in our heap. For some reason, CPU decides I will not store this particular count in heap yet, in our main memory yet, because I might still need it later. So let's go ahead and store this in L1 cache. So count is stored in an L1 cache. Okay. So even though the operation performed by thread 1 is completed, but still this particular count is stored in cache itself, right? So even if after completing this operation, thread 2 tries to read the value of count, the value of count will still be equal to 1, right? And still the increment on thread 2 will result in count equals to 2. Finally, when the CPU decides that let's now flush this value of count from cache to the main memory, at that particular time, the value of count will be updated in heap and the value will still be equal to what? Still be equal to 2, and it is still incorrect. So the second way in which this race condition can happen, even though the operation has been completed, is because of cache storage. Right. So what we have learned here is we have no guarantee after increment whether that particular value will be stored in L1 cache or L2 cache or L3 cache or will be flushed into the main memory. The time at which this particular count will be flushed in the main memory cannot be determined by us. Okay, it is decided by CPU. So this is also one of the reason due to which race condition happens. Okay, so the first condition was when simultaneously both the thread access it, and the second was due to cache storage. Okay, even after completion the value is stored still in cache, so there is no use. So still the value is not accessible to thread 2. The actual value of count is not visible to thread 2 because still that particular value of count is not flushed in the main memory. Okay, now let's go into our IDE, see one example of race condition, and post that we will see how we can actually force these values to be flushed in the main memory at our will so that all the threads can access the latest value of count. Okay, so what we are doing here is, so we have a class named shared counter. In that shared counter class, we have a variable named counter equals to 0, right? And we have getter and setter for that. In our printer1 class, what we have done is we have a variable named shared counter. The shared counter is initialized using a constructor of the printer1 class. And in our run method, what we are doing is we are incrementing the counter of shared counter. Okay, incrementing the counter inside the shared counter 10 times, right? So shared counter dot counter plus plus. Now in our main class, what we are doing, we have created an instance of counter. This will be initialized to 0. We have created two threads. In both of these threads, we have created an instance of printer1 and we have passed in the same shared counter variable that we have created here. Okay, so both of these threads will work on the same counter. We have started both of the threads. thread 1 dot join, thread 2 dot join. So we have commanded our main thread to wait for both of these threads to complete, okay, using this join method, and post that after the execution is completed, we have instructed our main method to print out the value of counter, okay, the value of this particular counter after the execution of thread completes. So what should be the possible output? So if I go inside printer1 will run this method. What it will do, it will increment the counter till 10, and print this thread 2. What it will do, thread 2 will also increment the counter till 10. So both are working on same counter objects, both are incrementing it 10 times, both are working parallelly. So counter will be incremented by 10, both using thread 1 and thread 2. So final value of counter, what it will be, 10 increments by thread 1, 10 increments by thread 2, output should be 20. Now let's go ahead and run this particular program. Yes, so our output is 20. Now let's go ahead and increase this from 10 to 100. Now what our output should be, both thread will increment the counter 100 times, so final value will be 100 plus 100, 200. Good, it works. Let's go ahead and increment it to 1000. 1000 plus 1000, 2000. This is also fine. Now let's go ahead and increment it to 10,000. What should be the expected output? 20,000. Let's go ahead and run this. Yes, see, the output should be 20,000, but it is not 20,000 here. It is 17,431. Let's go ahead and run it. This time it is 20,000. Okay. Again it is 19,232. This time it's 15,000. This time it is 20,000. So it is very random, right? Out of the 5 attempts that we did, 2 times it was 2000 and 3 times it was not 2000, it was any random value. This is what is called race condition. Now let's go into our whiteboard and understand why this would have happened 3 out of 5 times, okay? It could have happened 5 out of 5 times also. 5 out of 5 times this 20,000 could have been printed. 5 out of 5 times incorrect result could have been printed. Why this randomness is there? Let's go ahead and understand. So for the sake of our example, let's assume CPU decides that thread 1 will be running on core 1 and thread 2 will be running on core 2. Okay. And it also decides I will keep incrementing the counter for 10,000 times, but since the counter is accessed very frequently using this particular for loop, so let's not flush every increment of counter's value to main memory. Okay, rather than flushing it on every increment, let's flush the value of counter after every 100 increments. So what I mean to say is, thread 1 has read the value of counter, it has incremented it, but after suppose incrementing it from 1 to 2, it will not flush it into the main memory yet, because that will take time. Instead, it will just store it in either its register or L1 cache, because it again has to increment the same counter, right? So why bothering it to store it in main memory, then again fetch it from main memory, right? So it wants to make this particular execution faster. So it decides that once I increment it 100 times, so once the value of counter becomes 100, after that till that time I will store it in cache, and after it reaches 100, I will go ahead and flush it in our main memory. Okay, so this is what our CPU decides. Okay, now suppose what happens, suppose our counter reaches the value of 20. So at this particular point of time, thread 2 starts executing in parallel. Okay, so value of the counter will be read from the main memory for thread 2. What is the value of counter here? Value of counter is equal to 1, right? So since the actual value of counter, which is 20, is not yet flushed in main memory, so still counter equals to 1 is visible to thread 2, right? So thread 2 is still incrementing the stale value of counter. Okay, so if this keeps on happening, the final value of the counter will be less than 2000, right? So in the case of our incorrect outputs in our IDE, there was no guarantee when the values will be flushed in the main memory. Hence the counter was not reaching 20,000. Okay, and in case of correct outputs, it is very much possible that luckily CPU would have decided to read the value of counter from the main memory. Okay, read the value of counter from the main memory and flush the value of counter into the main memory after each and every increment. So 2 out of 5 times, luckily we got expected output of 20,000. Okay, but we cannot survive on luck, right? So what if we have a method wherein we can enforce the CPU to read and write shared variables from the main memory? Okay, so if that is the case, if we can enforce reading and writing of the shared variable into the main memory, then this race condition will be eliminated, right? All these caches will be removed from the picture, right? And all the values will be directly accessed and flushed in the main memory itself. Okay, so if we enforce that, race condition will be eliminated, and to do that we have two keywords in Java. One is synchronized and another is volatile. Okay, so if I what will I do is, so if I put this particular section incrementing the shared counter inside our synchronized block, then this particular race condition will be eliminated. How will this be eliminated? This is the property of synchronized block. What happens is, as soon as a thread enters a synchronized block, so suppose I write synchronized on this, and inside this shared counter dot counter plus plus. Okay, so this shared counter dot counter plus plus, it is actually a two-step process. Okay, so in first step process we read the value of counter. Okay, and in second step what we do, we increment the value of counter. Okay, so counter plus plus is effectively shared counter dot counter equals to shared counter dot counter plus 1. Okay, so at this particular point of time, counter is read, the value of counter is read, then it is incremented by 1, and after that it is stored in that counter variable itself. Okay, now there are two very important properties of synchronized block which helps in eliminating the race condition that we saw here. So first property is, as soon as a thread reaches the start of the synchronized block, all the variables which are visible to the thread, their latest values will be fetched from the main memory, and further operations will be performed upon those fetched values. Okay, so listen to this very carefully once again. So as soon as the thread reaches the start of the synchronized block, all the variables which are visible to the thread, their latest values will be fetched from the main memory, and further operations will be performed upon those fetched values. Okay, so at this particular point of time, what happens is, the first step is read the value. Okay, so at the start of this synchronized block, okay, so here what are the variables which are visible to the thread? So if you remember, we have initialized shared counter using our constructor. Okay, so shared counter is visible to the thread. So at the start of the execution, before starting the execution of the synchronized block, all the variables which are visible to the thread, their latest values will be fetched from the main memory. Okay, so value is fetched from the main memory. Okay, and the same can be, after fetching, the same can be stored either in L1 cache or register, it doesn't matter. So that value is fetched initially. Okay, and after that it is incremented. Now second property, as soon as the thread leaves the synchronized block, values of all the variables which are visible to the thread will be flushed to the main memory. Okay, so the first property was at the time of entering the synchronized block, latest value will be fetched, and at second property, at the time of exiting the synchronized block, latest value of all the variables which are visible to the thread will be flushed to the main memory. So if suppose the value of counter is initially 0, after going here, this 0 is read from main memory. The value of counter is incremented from 0 to 1 inside the synchronized block. Now as soon as thread 1 leaves this synchronized block, this incremented value will be immediately flushed into the main memory. Right, it will be immediately flushed in the main memory, not in L1 cache and not in register. It will be directly flushed into main memory. So when thread 2 tries to read the value from the main memory, that will be the latest value of counter that is stored, which is equal to 2. Okay, so if we use this synchronized block, both fetching the value of counter and flushing the value of counter, we have forced our CPU to do that using the main memory itself. Okay, so that is what synchronized do. So we have enforced the reading as well as the increment both to the main memory. So that is the reason both of these threads, thread 1 and thread 2, will get the latest value of counter and there will be no race conditions, right? Now let's get on our IDE and see whether this actually works or not. Okay, now let's go ahead. Let's write here synchronized. Let's synchronize it on our shared counter, right? And then try to increment this. Yes, the value is 20,000. Let's try and run again. Again it is 20,000. Again it is 20,000. Let's go ahead and do this to 100,000 and try to run it. Output is 200,000. Output is 200,000. Okay. So as soon as we use this synchronized block, all the increments have started going into the main memory, and hence we have avoided the race condition. Along with this synchronized block, there is one more keyword, volatile, that we discussed, that also has the same property, right? But whether this volatile will work here or not, right? If we put here volatile, whether it will work or not, I want you to write volatile here, remove this synchronized from here, and check if this actually works or not, right? And whether it will work or not, and if it does not work, why it does not work, if it works, why it works, that we will see in our next video. So that's it for this video. Until the next video, stay safe, stay healthy. Bye bye.